All right, all, here is a quick video for the first half of class since I forgot to hit record. Amazing on the last day. So our fun question was how many of the unit quizzes can be retaken during finals week? And if you notice, all of our answers are one. You can do just one. So you need to decide, which one that you want to do and then do that one. There's more information about this at the end of our video for the second half of class. So I talked a little bit more about the choice that you might want to make about that. So I'm going off of our filled in notes. So these graphs, I'm going to post the video that I made for my 8 a.m. class that walks through those. So you can take a look at that one if you want to see how to do those videos. I'm just going to use our filled in notes. I didn't want to erase and rewrite. So our limit here of this rational function, this goes to infinity. There's a couple of ways that you can think about this. I like to think about it as looking at what's happening with those leading terms. Sorry, I get leading term and leading coefficient confused in my head all the time. And those are our terms that have the highest exponent on the top and the bottom, because as x gets really large, our rational function, that x to the fifth on the top and the x to the fourth on the bottom, those are going to take over. And so as we get really large, our limit is going to be approximately the same as the limit of just that leading term on the top divided by that leading term on the bottom. And that's also why I put that approximately, because they're not equal. These two limits are not necessarily equal because those functions are not the same function, but they behave the same. So we can look at that simpler version of the function to say, okay, we're going to have x to the fifth over x to the fourth. Those cancel out, give us x. And this is going to go to infinity. If we wanted the algebraic method to do this, that is actually taking the top and the bottom of your function and multiplying it by the largest degree term on the bottom. So the largest degree term on the bottom of this rational function is that x to the fourth. So we divide every term by that. And so really what we're doing is just multiplying the top and the bottom by 1 over x over 4. And that's multiplying by 1. So we're not changing what our function is, but we're changing how it looks. And then we reduce each of those terms. So on the top here, that 1 over x to the fourth is still 1 over x to the fourth. The x to the third over x to the fourth reduces to 1 over x. And then we have our x to the fifth over x to the fourth, which gives us x right there. And then on the bottom, we end up with 1 over x to the fourth plus 1 over x squared, canceling our terms, and then a 1. And all of those terms where we've got x to some power on the bottom of that fraction, all of those go to 0, and we're left with x over 1, which is what we just had up above. This next one here, again, we thought about it the similar way that we looked at what was happening with those leading terms, the x to the 5x to the third and x to the third, and made a ratio of those because, again, as we get really large, that's what's going to take over, and those x of the third on the top and the bottom cancel and give us 5. And that's what our limit is. It is equal to 5. And some of you guys might know that if you have that the degree on the top is equal to the degree on the bottom, the limits were equal to the ratio of the leading coefficients. That is always true with rational functions. This previous example, we have the degree on the top is larger than the degree on the bottom, and we go to infinity, and that's true anytime the degree on the top is larger than the degree on the bottom. And that again also goes back to growth rates. The top of that function is growing faster than the bottom is. All right, this guy here, this one is true. And how we showed that that was true is that we took our e to the negative 2z and we moved that down to the bottom of the fraction and then realized, oh, we'd have 1 over e to the 2z. So we'd have 1 over a really big number. That's going to go to infinity. Same with 2 over z. That's going to go to infinity. The first term, where e is on the bottom, that's going to go to, did I say infinity? It's going to go to 0. That's going to go to 0 a lot faster because the bottom's going to infinity a lot faster, but they are both eventually going to go to 0. And so altogether, each thing is going to go to 0, so the whole thing is going to go to 0. So this guy here, we started by looking at what we got from plugging -1 into that function. We used that top equation because that's where our equal sign was, and we got 1. Then we also looked at that left-hand limit. So again, that is us traveling along the left-hand side of our graph. We did draw the graph after we did the left-hand limit, but we're on that x squared function coming from the left. So that's why we plugged it into x squared and got +1. When we're coming from the right, that's us traveling along this linear function, and we're getting closer and closer to where that open circle is, or what we would get from plugging -1 into that equation, and we get -3. And that also helped us draw this graph. But this also told us, because our right and our left-hand limit were not equal, it told us that our function, its limit as we go to -1, does not exist. And so this function, this piecewise function, has a jump discontinuity at -1. And I think that's a great word for it because we jump from the purple graph down to the green graph. We also talked about different kinds of discontinuities that you can have. And we talked about removable discontinuities, that's up here at the top. That's when we have a function, in particular, like a rational function where you've got a common factor on the top and the bottom that we could kind of, in quotes, technically cancel. But we can't because the original function has both of those factors on the top and the bottom. But what that does is leaves us a hole in the graph. And so we call it removable because basically the idea is that, boy, if we knew where that hole was, we could fill it. We could fill that hole and make our graph continuous there. So that's the idea of a removable discontinuity. This function also has an infinite discontinuity because it has an asymptote. And so an infinite discontinuity is just talking about, that we have that behavior that going towards a point on our graph, we're going to positive infinity from both sides or negative infinity, or it's doing the split where one side's going to positive and one side's going to negative. We also looked at how we would need to change this function so that this was continuous. So let me copy this and paste it. Oops, I don't want to paste it as an image. I want to paste it as just another graph. That we could take this graph that's sitting down here, and if we could move it up so that the 2 points meet up, we could make our graph continuous. So to do that, we'd have to figure out what that C needs to be. We can kind of see it from our graph, but what that C needs to be so that our two graphs meet up. So we took -1, plugged it in for x, and we need that output to be +1. So we then solved and figured out what C needed to be so that would happen. C needs to be 3. And that's exactly what we saw by moving that graph up. Let's see here. So this guy, whether this one is true or false. Oh, I didn't actually circle it. This one is true. So this one I tried on my own using L'Hopital's rule on, and it kind of ran me around in a circle and didn't get me anywhere. So instead, what I then looked at is, okay, we can look at this with the same reasoning we've been looking at the sort of regular rational functions and thinking about what's going to take over on the top of our function, what's going to take over on the bottom. What's going to take over on the top is that square root of x squared, so that x squared term. And what's going to take over on the bottom is that 2x. And if we simplify things down, that gives us a 1/2. And so that shows us, oh yeah, our limit is 1/2. Another tactic that you can take if you're not sure what to do is plug numbers in. Plug in 1,000, see what happens. And we got something close to 1/2. Plug in 10,000, see what happens. And see if it's equal to 1/2. This can also help you, if you don't know what it's equal to. It helps you when you're trying to prove something, whether it's true or false, or if you're just trying to figure out where to go and what to do with this limit. This one here, we have it set equal to negative infinity, but it actually goes to positive infinity. And the way that I looked at this actually was to make a little table and to look at what was happening on this graph as we went close to 5 from the right-hand side, so from values that were greater than 5. So I looked at what happens at 5.01, what happens at 5.001. And what happens is that we keep getting closer and closer to 10 on the top of our fraction, but the bottom of our fraction keeps getting smaller and smaller. So overall, our answer keeps getting bigger and bigger. So we're going to positive infinity. And then we talked about an intermediate value theorem question. So the thing about the intermediate value theorem is it's one of those things where it's like, this feels like this is really obvious, and it is. And the big key, and if you notice, I already have this underlined about 5 times there, is if your function is continuous on the interval you're looking at. So the first thing that I generally do is when I'm given an equation like this, I get everything all on one side because I actually like to look at it as that we've got that whole function there and I'm trying to figure out, does it have an x-intercept? I kind of like to look at it that way versus, does that one, that cubic function we have at some point equal -2? I just in my brain can think about it a little better if I'm looking at it as in terms of an x-intercept. So I usually get everything all on one side and say, okay, is this ever equal to 0? Because it's answering the same question as that original equation equaling -2. That happens at the same place with those two functions. So the first thing we have to ask ourselves is this continuous on our interval that they want us to look at? And yes, it is. It is continuous. It's a polynomial. And then we have to look at what happens when we plug in the first endpoint of that interval. So we plugged in 0, we got 4. We plugged in 2, we got -6. And so I actually over here started with those 2 points plotted, and then I talked about that because our graph is continuous, our function, we have to be able to draw the graph starting here at 0 and y value being 4, we have to be able to, and I don't know exactly what it looks like, and yes, it does not look squiggly like this, but it does something, and it has to be all connected because it's continuous. So at some point, it's going to cross the x-axis. Now, this graph probably does look actually something more like that, but at some point, it has to cross the x-axis because it's all connected. We did go back to this piecewise function that we had here and looked at it for a minute from, say, -2 to 0. So on this interval here, from -2 to 0, our endpoint here, we get +4, and our endpoint right here, we get -1. So if this was continuous, at some point our graph would have to cross the x-axis. It doesn't here though, because we're not continuous at -1. So it fails that very first condition of the intermediate value theorem. And the intermediate value theorem says this only works if our function's continuous. And here's why it breaks down. When you're not continuous, you can have a jump like that, and it doesn't cross the x-axis. So that's why we always have to check continuity. But yeah, it's definitely one of those things where it's like, yes, this seems like this is pretty obvious, but it's super powerful and it helps us realize, yes, we are for sure going to have that x-intercept in that interval. And now if I actually wanted to find out what that x-intercept was, is I would kind of start making that interval smaller and smaller. I'd maybe look at what happened when we plug in 1, what happens when we plug in 1/2, what happens when we plug in 1 1/2, so that I can, try to narrow down my search area. Because what the intermediate value theorem does is it basically kind of tells you that like you're on a little Easter egg hunt for x-intercepts. And it tells you there's an Easter egg out there, but it doesn't tell you where it is. So what you have to do is then sort of narrow that search area and figure out like that smaller and smaller interval if you actually want to find out where it is. All right, the last one I think that we did before the break was this guy here. And this one we just needed to use L'Hopital's rule twice on this. So again, your first step with doing these limits should be to check what happens when you plug in 0. We get 0 over 0. It's one of those indeterminate forms. So we took the derivative of the top and the bottom. We got negative sine of x over 2x plus 1. Then we plugged in 0 again to see what happens. Do we need to use L'Hopital's rule again, or do we get a number? We got a number, we got 0, and so that's what our limit was. And I'm pretty sure that I did this one in class on the video, so I think we're good now.